Oh, good morning, Chunk. Good morning, Walnut. Oh, I'm just studying for my topology qual. Well, I'm glad you asked. So the technical definition of a topology is that it's a set with a collection. You know, you're right, Chunk. We really should lay the foundations before we get started. Okay, so all you really need to know before topology is how to deal with sets and operations on them. I mean, knowing more isn't going to hurt you or anything like that, so I don't want to discourage, but it won't be necessary. In particular, the more you know about calculus and analysis, the better. What we're going to see is that even though it doesn't tell us the whole picture, different topologies often tell us when and how sequences converge. So if you already know about limits and Cauchy sequences and things like that, then you're already in a good position to take advantage of that knowledge. But if you don't know analysis really well, that's okay. All we need to know are sets and operations on them. So here's the idea. Basically, sets are collections of things. Ta-da! So why should we care? On a grand level, we care because set theory can be used as a foundation for mathematics. Seriously, if you just start with the idea that I can create collections of things, then you can build whole swaths of mathematics from scratch, topology included. Does that sound weird and abstract and hard to wrap your mind around? It does for me too. Just wait until we get to categories. Okay, so let's back up for a second. So sets are pretty much just collections of things. You can think of a set as a box, and the elements are the things inside the set, the things inside the box. We write sets inside of curly brackets, so if, for example, I wanted to write the set of all the positive real numbers, call it R+, then I would write R+ is equal to the set of all x's in R, the real numbers, such that x is greater than 0. But we don't even have to have sets of numbers. We can sort of have sets of whatever we want. The set of things on my couch right now is walnut, wine bottles, divorce papers. Walnut needs help right now, but he won't listen to me. Next, let's discuss the operations on sets. For notation's sake, we typically denote sets with capital letters and the elements of the set with lowercase letters. So the main operations we'll need to know at first are union, intersection, difference, complement, and product. So, given two sets A and B, the union is all of the elements in A or in B, or both, but we use inclusive or in these parts. The intersection is all of the elements in both A and B. The difference is just what it sounds like. A minus B is the set where we take all the elements of A and throw away the ones that were in B. A complement is just a special type of difference. We define the complement with respect to a universe. So if A is like all of these elements, then A complement is everything not in A, but everything has to be with respect to some frame of reference. For that reason, we usually don't write like A superscript C for A complement, because it's ambiguous, right? The complement is with respect to a universe, but what universe are we considering? So instead, we'll be explicit and say our universe is some set X, and then A complement is just the difference X minus A. And the product of two sets consists of a new set where the elements are now ordered pairs. Entries of the first component are just elements of the first set, and entries of the second component are just elements of the second set. Rather than a Venn diagram, a nice way to visualize the cross product is by imagining each of the factors as an axis, and then the elements of the cross product are just points in this plane. If you're solid on those, then you're golden. It might be worthwhile to play with these operations a little bit, and try and prove things like De Morgan's laws and other identities, but it's not necessary. Consider your first homework assignment to look up De Morgan's laws and then try and prove them, because we're doing homework now. Deal with it. Finally, I've been saying sets are basically, or pretty much, or sort of collections of things.
Basically, pretty much, sort of.
Because that's not entirely true. That's actually called naive set theory. Because you'd be naive to think that we could just willy-nilly create collections of things. Nothing is ever that simple. Why would you ever think that? You should be so embarrassed right now. Who would be that foolish? Well, Georg Cantor thought that. You might know him from his work of showing that there are infinities of different sizes, or you may know him from the fact that his contemporaries hated him so much that their personal attacks drove him to a mental institution. Kronecker called him a charlatan and a corrupter of youth.
Hey kid, you want to learn that there are infinities of different sizes? Careful, this shit hits hard.
And Wittgenstein, the latter guy, said that sets were utter nonsense. Join me as we laugh at them in hindsight. Ha ha ha. So what's wrong with naive set theory? Cantor basically invented set theory, and he said that sets were just collections of things. This seems like a straightforward thing to say, right? It seemed that way to Cantor, but don't trust this guy, he's crazy. Well, along comes a man named Bertrand Russell to ruin everyone's day. Russell realizes it's naive to think that we can just gather a collection of whatever we want and call that a set. Russell showed that naive set theory leads to paradoxes. If sets can be whatever we want, think about the collection of all sets ever. That's a set, I guess. It's the set of all sets. If we can have sets of whatever, we can have sets of sets. Actually, let's stop and think about this for a second, because it's really weird and we need to make sure that we're absolutely 100% on it before moving on. So let's call the set of all sets S. And let's go back to thinking about sets as boxes containing stuff. So, what sort of things are in our box S? Well, any set is in S. So, R plus is in S, as is walnut, wine bottles, divorce papers. Also, S is in S, since S is a set. S can be inside itself. That's kind of freaky, but that's okay, we don't kink shame here. Basically, if we ever say the set of, then that thing is in S. Is that okay? Make sure that it is before we move on. S contains any sort of set with any sort of rules that you can come up with. Sets can contain sets. Sets can contain themselves. This is all fine and dandy. Let's think about another set now. Let's call it P, for paradox. Let's put sets into P, but not any old set like we did with S. For P, we'll only put sets inside of P if they don't contain themselves. I think he's doing that because he's a dog, not because he's confused. But Walnut has a point. We should really see some examples of things that go into P. Remember, if something is in P, then it's a set, and it does not contain itself. So, walnut, wine bottles, divorce papers is in P, because it's a set and it does not contain itself. Also, R plus is in P. But S is not in P, because S contains itself. Things in P are sets, and they're only in P if they don't contain themselves. Okay, this seems all fine and dandy too, unless there was some sort of dramatic irony that was just about to interrupt me and throw a wrench. Is P in P, like S was in S? Well, either it is or it isn't. What happens if it is? If P is in P, there's a problem. P can only contain sets that don't contain themselves. How can P contain itself if P contains things that don't contain themselves? So it must be the case that if P is not in P, well then it should be in P, because it's a set that doesn't contain itself. But hang on, we just said there's a problem. So it must be the case that there's a paradox. So what are we supposed to do if our set theory is not on solid footing? Well, axiomatic set theory is not really the goal here, so let me tell you what we'll do. To avoid the paradoxes of naive set theory, we're going to develop a new set theory, where we take sets as we've used them thus far, and we'll add in a new axiom. Don't make paradoxes! Phew, glad we took care of that. So, sets and operations on sets. That's all you really need to start talking about topology. So the technical definition of a topology is that it's a set with a collection. Chunk? Walnut? Where'd you guys go?